think we are good. Yeah, we are definitely good. Okay. Good morning. Welcome back to the last lecture this week for Data 100. So today we're gonna, well, first, as always, join Slido. The QR code is gonna be on every slide also. So today we're gonna finish up the last installment of the modeling series. Okay. So we're going to talk about ordinary least square. I'll explain what that means in a second. There's going to be a lot of names thrown at you today. Okay. So far what we have seen is simple linear regression model, right? Where you have an intercept and a slope, right? You have a single feature that you plug in. And you use that to predict the response. We also have we talked about concept models last lecture, right? So that's the model where it always predicts the same number, right? There's no input to that model. It only predicts a response by looking at past response, and depending on what kind of loss you use, right? You take the average, a median, and then that's gonna be your prediction forever and always, okay? And so today, we're gonna extend the notion of these two models into something that's called a multiple linear regression model, okay? So first, some announcements. Your homework 4 is gonna be due tonight. Sorry, your lab 4 is gonna be due tonight, and your homework 4 is gonna be due tomorrow. As always, you can always check when your assignments are due on a website. Today, sometime in the afternoon, I'm thinking, if it's, I think it should be ready. Yeah, in the afternoon, we will release the logistics for the midterm as well as the slots for you to sign up at the computer-based testing facility. Okay. So please check Ed. It should be in the form of an announcement, so you get an email too. Okay. And last night we released the practice midterm on Priority Learn. Okay, so there's a post on Ed about it, but basically there are two kind of platforms that you can access the practice exam on. One is on Priority Learn. On that platform, you're able to generate a limited number of exams, okay? So there's randomizations, right? Sometimes in the exam of like order of choices and things like that, right? So you are able to generate as many variants as you can, as you want to. So you get to practice like things in different order. And then you get a feel of, how the computer exam format is gonna go. No, not timed. You can just go back and forth in your questions. However, there's another way to access the exam, which is on Priority Test. So on Priority Test, the exam is basically as close to the actual exam as we can get it to. It's gonna be timed 110 minutes. You have one attempt, okay, on that platform. But the exam content is the same. There's the same Spring 25 exam that we just implemented in this digital format, okay? So whichever one you wanna use or both, you can take advantage of those. Orientation quiz is also on Priority Test. So if you haven't done that already, I highly recommend you to do that. You also have access to all of our past exams on paper on the course website. Okay, go to resources and there's a table with all of the past exams. So if you want practice, there's plenty of. Okay, yes. Will there be lecture on the day of the midterm? I think no, but check the schedule. I'm pretty sure there's not. Yeah, that sounds pretty bad, right? You have to take the exam and lecture. Yeah, I don't think so. Any other questions on logistics and practice exams and all these? Well, hopefully many of your concerns will be answered in the logistics post, but if not, always feel free to ask on Ed. Okay. All right. So that's the announcements. Let's dive into the content for today. So we're gonna start with a new model. Okay. Well, not necessarily a new model, but it's a improvement or a generalization from what we've seen last time. You saw this expression last time, right? On the website. Okay. Sarah, can you tell whoever's putting it on the website that they should put it on the website? Yeah. Okay. Should be up there once the website people see it. Okay. So this is from last lecture, right? We saw this this model where your prediction is gonna be based on a bunch of features, right? Not just one, right? Like in the SLR model, right? It's gonna be based on in this case, P features, where P is some integer, right? So and then your prediction is a linear combination, right? Of these parameters, right? From theta 0 to theta p, scaled by these features, right? x1, x2, x3, etc. Right? So you can really see this is just kind of one step above the simple linear regression model, right? Where in there you have the first two terms, right? And then, but now we're just tacking on more terms. Okay. So for example, right, this is the example we talked about last time, right? We want to predict the age of a cat, then we can use the length as well as the weight of the cat to predict it, right? So we have two features, length and weight. Okay, and we denote them by x1 and x2. So these are, I'm pretty sure they're Josh's cat. Anyways, then your multiple linear regression model will look something like this, right? Your prediction is going to be theta 0 or theta naught, right? That's your intercept term, plus theta 1 times x1. That's the term that represents the parameter and the feature of length. And then we're going to have theta 2 x2, which is the parameter and the feature of weight, right? And then you take the sum of them. That's your prediction. Okay. Well, so today we're going to use a different data set that you probably have seen in data 8 to always give you some numbers to work with. Okay. So this is the MBA data set. Our goal is to predict the average number of points a player scores across the season. Okay. So PTS, that's what it is. Okay. And then the features we're going to use, there's a short explanation on the right of what they are, but FG, AST, and 3PA. So field goals, assists, and 3-point attempts. Okay. So those are the three features we're going to consider to build our model. All right. So let's take a single observation. Well, okay. As an exercise, I guess this is going to be tested on our exam. Anyways, what is the granularity of this data set? Right? What does each row represent in this data set? Yeah, a player, right? So say I take row 2, right? That's the data for the second player, right? Then I can take the value of this player's features, right? 0.4, 0.8, and 1.5, as well as the true response, right? PTS, which is 1.7. Okay. So to generate the prediction, what I'm gonna do is I'm gonna compute a linear combination of my parameters. In this case, I have 4 parameters, right? 1 intercept plus 3 thetas for 1 for each feature I use, right? So I'm gonna have a total of 4 parameters. I'm gonna compute a linear combination of them, so theta naught plus theta 1 x1, right? In this case, x1 is what? 0.4, right? If you assume that it goes in order, right? And then x2 is going to be 0.8, and then x3 is going to be 1.5, right? So we scale the thetas by these feature values and then add them up, right? That's going to be my prediction. Okay. So later, right, we'll talk about our goal then is going to be finding these thetas, right, that would minimize some kind of loss we choose. So today, the loss we're going to choose is going to be the MSE, right? We're going to exclusively work with the MSE because it's nice, okay? And just to note that this particular combination of the multiple linear regression model under using the MSE as the loss function is called the ordinary least squares, okay? Why is it ordinary? Well, this is actually the most kind of fundamental model, the most fundamental problem in this linear modeling realm. Okay, that's what's ordinary about it. But you'll see that nothing about the math behind it is very ordinary. It's very beautiful. Okay, and then solving for the thetas, right, that optimize, that minimizes MSE, right? We call it solving the OLS problem. So this is a problem that's waiting to be solved, right? And we find the thetas, right, that minimize MSE. We have solved the OLS problem with whatever data we have. Okay. So we'll first focus on the first two steps of the modeling process, and then we'll get to fitting the model. The reason we have to do a little bit of work is because I have a lot of features, right? So in this general model, right, where I have P features, I'm gonna have P plus 1 thetas to find, right? And doing it one by one is quite tedious, right? Of course, you can do it like you did in the SLR model, right? Where you take the partial of each one and you solve them all together. That's fine. But we're gonna use linear algebra to help us speed up this process. We're gonna do a vectorized operations where we can solve all of these thetas at once, okay? And that requires rewriting our problem in a matrix or product of matrices and vectors form, okay? So you will see this expression pop up a lot today, and then I'll explain what that means in a second. Okay, so just to review and compare a little bit, for our simple linear regression model, this is going to be our data set, right? We will have a single feature, right, x, and then we'll have a true response column, y, right? So today, right, whenever you see x and y without a subscript, usually is used to denote the entire column, right, of that feature, okay? So for our MBA example, right, we could use FG, right, field goal as a feature, right, and then PTS is our response. In comparison, if we have a constant model, right, then our data set is simply going to be that response column, right, the column of the y's, right, because I'm not using any feature in my constant model. And for then my multiple regression model, I'm going to put all of my features, right, in my data set. Okay? So I'm going to put field goal, assist, and 3-point attempts, right? Those are all going to be in my data set along with PTS, right? The response I'm trying to predict. Okay. So there's a lot of notation here. Hopefully you remember how to represent entries in a matrix, right? So say I want the entry in the first row, right, and the second column, right? That entry is going to be denoted as x12 or whatever your matrix is, right? So in this case, it's x, right? So row goes first, column goes second, and then you also see on top here we have the right, the labels for each column, right? This is kind of following the syntax of pandas, right? When you're slicing into a data frame in pandas, you're saying, okay, give me everything in the row. Sorry, give me everything in the first column, right? Yeah, but this is not Python, so your index starts at 1 instead of 0, right? So you see this x subscript colon comma 1, right? That just means that you're looking at the first column of this matrix or this table, okay? And then x colon comma 2, that's a second column, okay, etc. Okay, then let's compare this. Let's put this in our context of the MBA data again. All right, so say I want everything in the first row that would represent, right, observation 1, right? Or in general, if I want observation I, right, in the MBA example, I want the data for player I, right, the ith player, I just pull out everything in the ith row, right? And those entries are going to be xi1, xi2, right? Because, right, the first number in the subscript represents which row you're looking at, right? So xi1, xi2, etc. And then yi in the end. That's my response. Okay. What if, say, I want the second column, right? What in my data set represent what assists, right? AST. That's the column that I want. But in this matrix notation, what would be the entries that I pull out if I want the second column? What are the entries? x12, x22, all the way to xn2. Right? So if I want the ith column, I will get x1i, x2i, x3i, right? Because the second index represents what column I'm looking at. And the columns represent the feature, right? So the rows represent the observations, the columns represent the features. Okay, that's how you read a matrix that looks like. Okay, well, then what I can do is I have my model, my multiple linear regression model. Then I can make a prediction for each observation, right? I have all the notations for it. Then, right, the prediction for the first player, y1 hat, is gonna be, right, my parameter, my slope theta naught plus theta 1 x11, right? That's the first entry in the first row, plus theta 2 x12, right? That's the value for a second feature for that observation, etc. And then I can do that for every single row, right? Then I'll have m predictions, right? That are functions of the feature values for those observations. Seems like a lot to write out, right? Every time you have to do this, and then you have to do, or you have to write out each row explicitly. Let's use linear algebra to kind of make this a little easier. So quick review of a linear algebra concept, dot products, or because we're working with in the real space, inner products, they're the same in any real space, right? So these are operations that will that work with two vectors of the same length, right? They have to have the same entries, same number of entries. Okay, so for example, I have two vectors here, u and v, right? So 1, 2, 3, and 1, 1, 1. If I want the dot product of these two vectors, this is u dot v, or the dot product between u and v. What I can do, right? What this operation does is it takes the corresponding entries in the two vectors and then multiplies them and then adds them up, right? So let's work on the first entries in the two vectors. That's 1 and 1. So you multiply 1 by 1, right? Second entry is 2 and 1. So you multiply 2 by 1. And third entries are 3 and 1, right? So 3 times 1. And you add these up, right? So the dot product between u and v is 6. Whenever you take a dot product, your result is always going to be a number, right? And sometimes if we just want to work with arbitrary vectors, right, we can write this as a product between U transpose in V or V transpose in U, right? So when you're taking the transpose of U, what you're doing is instead of writing out the vector vertically, right, that's a 3x1 matrix, you're going to write it horizontally. So that's a 1x3 matrix, right? So that's what U transpose is, right? So dot product between two vectors is one vector transpose times the other. And you just follow the matrix multiplication rule, okay? Row times column. All right. So why do we bring this up? Because if you observe our predictions, right, which are linear combinations, well, this looks like a dot product if I put all the thetas in a vector and all the x's in a vector, right? And if I take the dot product between those two vectors, I should get back this prediction, right? So let's ignore the theta naught for a second. We're gonna come back to it. If I put all the thetas, right, theta 1 through theta p, and all the x's, x1 through xp, in two vectors, I take the dot product of those two vectors, right? Then I get back my, then I get back the expression from the top, right? They're equal, they're the same. But now I can write it as a dot product of two vectors, right? If I give those two vectors each a name, then I don't have to write out the entries every time, right? And now let's deal with the theta naught. Ideally, I want to add theta naught into that vector as well, right? So, but it's not being scaled by anything in the linear combination, right? At least it seems so. There are two numbers that are often ignored in math that are critically important. So even though it looks like it's not being scaled by any number, what is it actually being multiplied by if you want to put a number after theta naught? Exactly, ones and zeros. Sometimes you don't see them when you write out an expression, but they're there, right? So what I can do is I can add a 1, right, to the scaling factor of theta naught. Then I can put theta naught into my theta vector and then just add a 1 to my x vectors. And then this looks a lot nicer, right? I don't have that one kind of long term, right? It's sticking out. Okay? This 1 is often called the bias term or the intercept term, right? Because that's a term that's corresponding to the intercept. Why is it called bias? You'll learn about it in a couple weeks when we actually talk about what a bias is. Okay? And now if I call my theta vector theta, my x vector x, right? Remember, without the subscript, usually today, they will just, these letters will just represent an entire column, okay? And then usually we write x first. So this is going to be the dot product between x and theta, right? Or x transpose times theta, okay? So now, in writing out each prediction, we can simplify it, right? By writing them in dot product form, right? So my y1, the prediction for the observation is going to can be written as x1 transpose times theta, right? Theta is still your vector of parameters, right? But x1 is really that first row of our data set now, right? The x1 transpose, right, is the first row of the data set plus this 1 in front, right? y2 hat can be written as x2 transpose theta, right? Where x2 transpose is the second row of our data set, the second observation, plus a 1 in the front, right? And then you take out the y's, of course, right? We don't want the y's to be in the predictions. If you know the y already, why would you even bother using these x's, right? And all of the thetas are the same, right? Because we want to fit just one set of thetas for all of these and for new data points as well. Okay. So say, for example, in my NBA data set, I want to write out a prediction for the second observation, right? Then my x vector, my x2 is going to be 1 is going to be just the second row, right? Minus a 1.7 with a 1 in the front. The true response y2 is 1.7. My thetas are just arbitrary thetas, right? That I haven't fitted yet. And then I can write it in this dot product of 2 vectors. Okay? And whenever you're doing linear algebra, it's always a good idea whenever you work with matrices vectors to check the dimensions. So that when you multiply, say, matrices or matrix and a vector together, the dimensions match up. So that's a good basic check for your calculations. Okay, so let's check the dimensions. X2, right, has 4 entries. So there's an element of R4. And then theta also has 4 entries. They're all real numbers as well, right? We just don't know what they are yet. Right. So y2 is a real number, right? And y2 hat is also a real number, right? So those two are just a single number, or just single numbers, and they're also called scalars, right? As opposed to vectors. But when you're working with kind of matrices and vectors, you can always think of a scalar as a 1-by-1 matrix, right? Sometimes it makes things a little easier to think about. Okay. All right. So before we write out our final kind of aggregation of these data points, any questions on what I've talked about so far? Yes. Yes. So the 1 comes from this, right? Because I want my theta naught to be in that theta vector as well. So implicitly, I'm multiplying theta naught by 1 in the linear combination. Yeah. Often easy to forget that 1 when you make this when you put these in a matrix, but weird things start happening when you don't put in that intercept. We'll see later today, kind of a little bit of intuition on that. Okay. Okay. So now let's not stop here because now I still have n separate expressions. I want to put all the expressions into 1, right? So what I'm going to do is I'm going to attempt to put all of these in a matrix. Again, these are typed out on the slides. I just like using the board so you can see step by step how things happen. Okay, so I have my y1 hat, right? This is going to be, right? Let's write out the x1 transpose. So there's going to be 1, x11, x12, dot, 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 to x1p, right? This thing times, I'm going to write this a little weird, my thetas, right? Theta naught, theta 1, theta 2, dot, 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 theta p. Okay. So, right, my y1 is going to be the dot product, the product, right, between these two vectors, where you get back to your linear combination that you want. What about y2? This is 1, x 21, x22, x2p, right, times the same theta vector, right? Now you see why I'm writing this kind of weird in the beginning. Okay, and then it goes on and on all the way to yn hat, right? So that's going to be 1, x n1, x n2, x np, right? Okay. So I am trying to, instead of working with each individual y hat, I want to put all of these y hats in a vector, right? So I just have one vector that I can name then whenever you see that name, you just know that's the vector of all the y hats. Okay, so if we observe what we have here, right, is the first entry of this vector, y1 hat, it's gonna be, right, this x1 transpose times this theta. The second entry is gonna be x2 transpose times theta. That kind of like works like a matrix multiplied by a vector, right? Row times that vector. This is gonna be the first entry, right? Second row times the vector, second entry, right? So then what I can do is I can put all of these entries into a big matrix. And you can verify, right, that this matrix times this vector is gonna be equal, right, to the vector of the y hats on the left. Right? So instead of writing out each vector multiplication, now I have a matrix vector multiplication that would encapsulate all of the y hats. Okay? Does that make sense? Yeah? Okay. Again, the reason I want to do this is just I want to operate on everything at once instead of doing each row separately. Okay. So we have done it. We have put things into a big matrix, and this matrix of all of these features plus the ones, this is called a design matrix, right? This is a matrix with all of the features that you're using to predict the response. Okay? The dimension, right, of this design matrix is p plus 1, right? Because it has the n by p plus 1, right? Because you have n observations, n rows, and then p columns plus this one column of just ones, right? So p plus 1 columns. Okay? All right. So again, right, if we compare that to our MBA data set, now we have added the column of ones, right? We call it the bias column. Right? Each row represents an observation, each column represents a feature. Right? And then this one column of only of all ones is the bias or intercept column. Okay? And because now we have a matrix, we can name this matrix. We usually name it X, and then because it's a matrix, it's bolded, right? So, and then we'll name this vector of all y's, all y hats in bolded form. Somehow this is not bolded. This is theta. That's just the convention that this class has chosen, I guess. So whenever you have your multiple linear regression model, you can always write it in this form as well, instead of writing out each individual equations, right? Y hat is equal to x theta, okay? And you can check that the dimensions work out, right? My x has dimension n, has size n by p plus 1. And my theta is a p plus 1 vector or a p plus 1 by 1 matrix, right? So when you multiply x and theta, you will get a n by 1 matrix, or n, right? A vector with n entries, right? So that's exactly what y hat is, right? Okay, so make sure you check all the dimensions. I didn't do a good job of writing them according to size because this looks the same as this, right? But this has p plus 1 entries, and this has n entries. Okay. All right, so let's do a quick Slido. After all these kind of linear algebra stuff. Oh, before we do the Slido, I forgot to mention one thing. So things look a bit complicated today, not because they're conceptually intense. It's because we have so many notations, right? So many new notations that we have introduced. And whenever you work with notations, the only way to work through it is patience. Sit through all of the notations, ask yourself, what does this mean? What does that mean? Put the pieces together, right? So don't get too frustrated on your first go. just take some time to dissect these notations. Anyways, so here's a new definition. I need to move this a little bit. Okay. So we say an expression involving thetas, right, is linear in theta. It can be written as x theta, kind of like our multiple linear regression model, where x is a matrix that does not depend on theta, and then theta is just a vector of all the thetas, right? So if you can write an expression in this form, then we say that this expression is linear in theta. Okay? So the Slido question is going to be, which of the following five is or are linear in theta? Okay, so take some time, talk to your neighbors, see if you can write the expression in the form above, and then we'll talk about it. And then I'll answer any questions if you have any. What about now? Is it better? Is it working? Yeah. Good. Right. I can see my audio thing going up, so I hope it's working. Yeah. Good. Okay. Perfect. All right. Sorry about that. So norms. Okay. Let's do this. We're gonna talk about MSE, right? How to get the MSE into a linear algebra format that accommodates, right, our rewritten expression of the multiple linear regression model. Okay, so norm is a quick linear algebra review. Norm measures usually the size, the length, the magnitude of a vector. And the two norms we'll work with in data 100 is L1 and L2 norms. So today we'll work with L2 norms specifically. Okay, so if you have a vector, right, x, that's x1, x2, all the way to xn, so you have n entries, then the L2 norm of that vector is computed as the following, right? You square each entry of that vector, sum them up, and take the square root of it, right? Taking the square root puts things back into their original units, right? That's why we want to do it. Okay, so that is the L2 norm. Okay. It's a generalization of Pythagorean theorem, right? Because if you look at the first two entries, that's literally what Pythagorean theorem is, right? You have the two edges of a right triangle, and then you're looking for the third one. Okay? So that's the norm with a single vector, right? We can use this L2 norm to measure how long a vector is, to measure the magnitude of it. Anyone remembers? What are the two components of a vector? So magnitude is one, and then the other one is direction, right? So it doesn't matter where it sits in space, right? What defines a vector is magnitude and direction, right? So for a vector, right, a two-entry vector, AB, right, is length, it just is L2 norm, right? A squared plus B squared square rooted. Okay? Or if we have two vectors, we can use the L2 norm to calculate the distance between the two vectors. Okay, so you have vectors A and B, then the distance between A and B is just the L2 norm of A minus B, right? When you subtract two vectors, you get a vector, right? You take the norm of that, you get a number, right? That number is the distance, right, of the two vectors. Okay? And we like the square root because it gets rid of the, it makes the units nice, right? Back into the original units. However, sometimes square roots are not the nicest to work with in math, right? So we like to square the L2 norm sometimes just to get rid of that square root, right? So we can do some calculations. All right, so what does that have anything to do with my MSE then? Well, if you compare the mean square error with the L2 norm, right? In that definition, if you replace xi by yi minus yi hat, right? Then what do you get, right? Ignoring that 1 over n, right? What you will get is the L2 norm of a vector where the first entry of the vector is y1 minus y1 hat. Right? Second entry of the vector is y2 minus y2 hat, etc. Right? Let me quickly write this out so you can see that they're indeed equivalent, right? So so here's my y vector as y1, y2, way to yn. Right, here's my y hat vector, y1 hat, y2 hat, yn hat. Right, if you subtract them, what you get is right? y1 minus y1 hat, y2 minus y2 hat, yn minus yn hat. Right, so that's what you get if you subtract them. And then if you take, right, the L2 norm, and then you square the norm to get rid of the square root, right? This is going to be, right, you square the first entry. So y1 minus y1 hat squared plus y2 minus y2 hat squared plus all the way to yn minus yn hat squared, right? So you will get yi squared, right? So this is just a way to write the sum in as a norm of a vector or squared norm of a vector. Okay? Now, right, then because my multiple linear regression model is y hat equals to x theta, right? So I just replace the y hat by the x theta. Now I have my MSE in terms of theta, but also in this nice vector form, well, norm of a vector. Okay. So based on this, all right, let's do another Slido. Which of the following are valid interpretations of the OLS problem? So I have three choices. You can also choose all of them or none of them. Okay. So take a second, talk to your neighbors. Right. I should have put I'll write the expression on top again, so you can have reference in. Okay. Let's talk about these. Okay. See the results. All right. Overwhelming majority that chose D, right? All of them. And let's see if that's the case. Well, should do animation here to add to the suspense. But anyways, yes. So all of these are valid interpretations, right? A, right? That is following, right, our modeling process, right? Where our model is a multiple linear regression model, y hat equals to x theta. And our goal, right, our loss is MSE. So we're minimizing the MSE under the multiple linear regression model, right? Well, for B and C, remember how we wrote we were able to rewrite the MSE, right, into this form, right, involving y minus y hat, right, this vector right here, right? So to minimize the MSE then is to minimize that norm, right? And how can you interpret that norm? Well, remember, norm of a difference of two vectors, that's a distance between those two vectors, right? So we can interpret that as minimizing the distance between y and y hat, those two vectors. Or if you regard that y minus y hat as a single vector, as we have done here, right? And then this vector has a name, is called a residual vector, right? Because it incorporates all of the residuals, right? And we use the letter E to denote it, right? So if we regard this y minus y hat as a single vector, right? Then what you're minimizing is just the norm of that vector or the length of that vector, right? Because that's what L2 norm is. Okay? So any questions? We're gonna go on a break right now, but any questions before that? Okay, so let's take a 2-minute break, or I guess 1 minute, because we're actually a little bit behind schedule, just a little bit. So take a minute and then we'll reconvene. Okay, let's keep going. You can see me. If you were here earlier, you saw there's a ridiculous Home Depot bucket. I'm not taking any credit for this. This is Josh's design. But we're gonna we're gonna do now. Let me explain why. We're not building or we're not painting anything. What we're gonna do is actually to fit the model. Oops. Right. So now that we have chosen the model and the loss, we can actually fit it. As I mentioned before, of course, right, you can still do where the calculus way, where you take the partial derivative with respect to each theta, right, and then set it to 0, solve for all of them. But that's quite complicated, right? There are too many terms. And also do some matrix calculus, which is beyond the scope of this class, but that's also viable. But what we're gonna do today is to build a geometric model that solves this OLS problem, okay? Anytime you work with linear algebra, just remember, most of the linear algebra concepts do have a geometric interpretation, a really nice one usually. So try drawing pictures whenever you work with vectors and matrices, okay? We're gonna help you build a picture today. So this is where we start. So imagine I have a this is my design matrix, right? I only have two features. First feature is the bias. Second feature is just some feature, right? And I have my responses, y1, y2, y3. So traditionally, if we were to plot my data, what I would do is I plot the xy pairs, right? So x1, y1, x2, y2, x3, y3, right? But these are my matrices and my vectors, right? I can do whatever I want with them. So instead of plotting each row, right, each pair of x and y, I'm gonna plot each column. That's also allowed, right? I have 3 entries in each column, so I'm gonna need 3 axes, right? And then we'll call these the row 1, row 2, and row 3 axes. And then my first point would just be 1, 1, 1, right? That's a point. That's sitting in 3-dimensional space. Second point is x1, x2, x3, etc. So on the right, this is one, because I don't know what the x and y's are, but just pretend that's what they are, right? So we have 3 points, right? Each with 3 coordinates. That's allowed, right? Okay, so with this, we're gonna do another quick linear algebra review about spans, okay? Let's talk about what a span is for a second. So let's say I have a vector here, right? My vector is pointing this way, right here. If I'm only allowed to multiply this vector by a constant, what points can I reach? I can make this vector longer, right? So I can reach points over there. I can make this vector shorter, so I can reach points here. Or if I multiply by a negative number, I can flip this vector and go the other way, right? So the points I can reach by multiplying this one vector by any constant is this line, right? That goes beyond, above and beyond on both sides. What if I have 2 vectors? And my only allowed operations are multiplying each vector by a constant, or adding these 2 vectors together, or I can do both, right? I can first multiply each vector by a constant and then add them, okay? What points can I reach? Yeah. It's a 2D plane, right? You can imagine I'm like spinning like Saturn, right? So I reach everything in this plane, right? If I'm allowed to do adding or scaling by constants. And this is essentially what I'm doing is I'm taking linear combinations, right, of these 2 vectors, right? And every point that the linear combinations of these 2 vectors can reach is called a span of these 2 vectors, right? It's a set of all linear combinations of whatever vectors you have, okay? So why did I bring this up? Well, we can regard the columns of a matrix, as vectors. Each column is a separate vector, right? That's what we did here, right? Each column is a separate vector. And these are called column vectors, right? Because they're columns and we look at them as vectors. And what I can do is I can look at the span of these vectors, right? Of these columns of the matrix. This is called the column space of a matrix, right? It's a set of all linear combinations of all of the matrix vector, right? Or the span of the matrix is a column vector, right? And then for short, we just call it span of X, right? So on the right, if you use our design matrix, which only has 2 columns, right? Then you have 2 column vectors. And you can imagine that this plane is a plane that's spanned by these 2 column vectors, okay? Of course, we can go higher in dimensions, right? But it's not as easy to visualize, so we're just gonna assume that we have a plane, right? That's a span, and we're gonna add a 3rd dimension later for something else, okay? Continuing with this idea, we're gonna talk about, what is the thing called? Sorry. We're gonna talk about matrix vector multiplication. I keep saying this word and then I forget. Matrix vector multiplication. in another perspective. Okay, so I have it written out right on my board here. I also have it on the screen, so whichever one you want to look at, that is fine. So when I multiply, right, this design matrix by the theta vectors, what I'm doing is I'm doing, right, first row, right, times this column, right? So element-wise multiplication, add them up. Second row times this column, etc. However, if you notice what you're doing here, right, the result of multiplying the first row and this vector is going to be theta naught, right, plus theta 1 x11, theta 2 x22. And the result of multiplying the second row, this vector is going to be theta naught plus theta 1 x21 plus theta 2 x22, etc. So the first term in the sum is always in terms of theta naught in both multiplication cases, right? The second term in that sum, right, in each multiplication, is always going to be theta 1, right? If you are a bit confused on what I mean, write this real quick. And right, so the first term, right, this is theta 1 plus theta naught plus theta 1 x11 to x22 plus etc. And the second one is theta naught plus theta 1 x21 to x22 plus etc. Right, so you see that the first term in each sum is always theta naught. The second term in each sum is always in terms of theta 1. Right, so what I can do is viewing this matrix vector multiplication as a linear combination of the columns of my design matrix, right? I take the first column, I scale it by theta naught, or in my slide above, theta 1, and then I take my second column, I scale it by theta 1. Right, so I'm taking linear combinations of these columns because remember, linear combination works on vectors, right? It's a general concept, right? So instead of doing row times the vector, I'm doing columns scaled by each entry of that vector. It takes a little bit of time to get around this idea, but as an exercise, you can kind of show that these two are equivalent ways of multiplying a matrix by a vector. Okay? If you're not convinced, just write it out yourself, and hopefully after a couple tries, you should be convinced here. Okay. So why am I bringing this up? Well, here's the deal. All right. My let's see. So my prediction y hat can be written as x theta. And now we just saw that x theta, right, a matrix multiplied by a vector, can be written as a linear combination of the columns of x, right? And what does the linear combinations of the columns of x make up? It makes up the span of x, right? So my y hat, which is the linear combination of the columns of x, just saying that really quick because there's so many words. My y hat is going to be in the span of x, right? So, right, these are my two column vectors for x, right? This is a space spanned by x. Then my y hat is somewhere in this space, right? It cannot go anywhere else. But my true response y, right, in comparison, does not have to sit in this space, right? Does not have to sit in the span. It can be anywhere, right? It's my true response, right? I don't know what is going on with my true response, so it can go out. So here's where our model comes in. So you would imagine, okay, let's see if Josh has left me with the right instructions on how to build this. Okay, so you can imagine that these two longer ones are my column vectors, okay? And then they sit in a plane, right? They sit in a plane. That's this table, right? And then my true response y is this shorter one that I'm gonna make longer. There we go. Okay. Ignore the chain for a second. It has its use. Interesting. Wait. Oh, there we go. Okay. All right. Stay. Okay. Good enough for me. All right. So again, right, these are my two columns. It's maybe a bit hard to see, but they're on this table. And this stick going up is going to be my true response, right? Because this y vector, the true response does not have to be in the span of the columns of x, right? But my y hat, right, the column of the predictions is going to be in a span. It's going to be on this table, right? So what are we doing here? Is we're looking for a vector on this plane that is the closest to this vector of the true y, right? Because I'm trying to get as close as to the true response as possible. So that brings the question, where is that vector then on this plane? Is this vector somewhere? Where is it? Is it somewhere here? Where is the vector on this plane that's the closest to this? You can imagine that there's like a light bulb going up here, right? I'm trying to find a point on this plane that's closest to this light bulb. What do you do? On this plane? Yeah. Orthogonality, okay, let's, we're in less technical terms. I'm just casting a shadow of this vector onto this plane, right? And wherever that shadow lands, that's gonna be the point, right? Let's see if I can get that. Yeah, roughly, right? Wherever the shadow lands, right? That's gonna be the point that is the closest to this vector. Or the orthogonal projection of this y vector onto the span of x. All right, so let me put, so wherever this chain is landing, right? Because I'm just dropping this chain straight down, and it should land somewhere here, right? And then that's my vector, right? This is my response vector. It's like, it's here, but it's kind of hard to see. Okay, ridiculous, but if you can remember this picture, then this is successful, okay? So this is just repeating what I'm saying, right? I'm trying to find, right, the vector on this plane that's the closest to my y. Okay. Another question, right? Yes, I'm dropping my chain down here, and then this is my y hat. What is this chain? What does this represent? Why do I have a chain here? So just putting a vector here. What does this part represent? Perpendicular, okay. So it is perpendicular to the space, right? It's the error, right? This is my y. This is my y hat. Right? So this is the error of my prediction, my residuals. Eh? Good. So, and recall, what do we want to do with this ordinary least squares, right? We wanted to find, right, the y vector or the y hat such that its distance to y is minimized, right? And this y hat has to stay in this plane, right? So, and we have done precisely that, right? Where the orthogonal projection is, right, of this y onto this span of x, that's going to be where my y hat is, right? Because this distance, y minus y hat, is minimized. Okay. And the other thing to note, right, is because we have orthogonal projection, right? What does it mean to be orthogonal? Well, two vectors are orthogonal to each other, right? So A and B, they're orthogonal to each other if their dot product is 0, right? So A and B are two vectors that are orthogonal to each other. So A transpose B is going to be 0. And we can also use the word orthogonal, or basically just perpendicular, right? But orthogonal is more widely used in text. Okay, so we can also use the word orthogonal to describe a vector with respect to a plane or a space, right? A vector is orthogonal to, say, the span of M, where M is a matrix, right? If and only if this vector is orthogonal to each column of X, right? Because that makes up the span of each column of M, right? Because that makes up the span of M. Okay, so if V, right, is orthogonal to M, right, that means that, right, the first row, the dot product between the first column and V is 0. Dot product between the second column and V is 0, and etc. Or if you want to write all of these expressions in one go, right, in matrix form, right, M transpose, I'm making the columns the rows, right, so I can multiply them with a vector, right? M transpose V is going to be the 0 vector, right? Running out of time, so I'm going a little fast. Feel free to read these slides after lecture, because I do need to get to kind of the punchline here. Okay. So in our case, right, our y minus y hat is orthogonal to the space of that is the span of X, right? So y minus y hat orthogonal to span of X, or right, y hat is X theta. So y minus X theta is orthogonal to the span of X, right? So here my X is playing the role of my M, right, in the definition from the last slide. And then my X minus X theta, right, which is a vector, is playing the role of V in my definition from the last slide. Okay? So using this, we can actually solve for what the optimal theta is. Okay? And I guess we will, this is where we end today. Well, after this calculation, not like right now. Okay. So, right, I know my X, start my, well, my y minus y hat, right, or y minus x theta hat, dotted with x transpose times this residual is going to be 0, right? So let's solve this for theta. X transpose y minus x transpose x theta hat 0, right? And then x transpose x theta hat going to be x transpose y. So I'm just moving this to the other side. And remember, whenever you have vectors and matrices, when you multiply, multiplying by on the left and on the right are different, right? There's left multiplication and right multiplication. So I want to move this x transpose x to the other side. What I'm doing is left multiplying by the inverse of it, provided that an inverse exists, of course, right? By x transpose x inverse on both sides. And that's what my minimizing theta hat is. It's going to be a vector, right, of p plus 1 thetas. All right. So this is going to be kind of the punchline of the lecture, right? In one intermediate step that's quite important is from here to here. Okay, this step is so famous that it has its own name. This is called the normal equation, and this is called a solution to the OLS problem. Okay, so important of a result that it deserves its own slide. So whenever you have your design matrix X and your response is Y, this is what your theta hat is going to look like. Okay. So I don't think we'll have time to go over the OLS properties. So what I'm going to do is, well, the slides are going to be on the website. I'm going to make a short recording of the last bit. It's not going to be that long. It's like 15 minutes. So you can watch on your own time, or you can read the slides. Okay, I'll post them by the end of today. So you have time to review them and, do your homework and labs. Okay. All right. I will see you next week.